So welcome everybody to a distinguished public lecture of ICTP-SAIFR. So thanks everybody for coming on a Saturday. So I'll say a few words about our center for people who don't know it. This is the first time. So it's called ICTP-SAIFR. It's connected with an international center in Italy called ICTP. SAIFR is South American Institute for Fundamental Research, but we concentrate on theoretical physics. And this building is the Institute for Theoretical Physics, Instituto de Física Teórica of UNESP. The director of UNESP is Alexandre Rocha, who's there in the audience. So almost all of our activities are here in this auditorium. We have lots of kinds of activities. So we have activities for high school students. So for example, this morning we had an activity for high school students, and every Saturday morning directed by Lucas David. And many of the high school students are here, which is great. And of course, if you know high school students that might be interested in participating, all the information is on our webpage. We also have activities for high school teachers, for the general public. So this, of course, is an activity for the general public. Most of our activities for the general public are in Portuguese. But this is, of course, in English, but it will be transmitted on YouTube and then recorded, of course, and we'll put subtitles in Portuguese. So as I said, we have lots of activities for the general public. The next activity we have is next week. Actually, last week we just had an activity related to the film Oppenheimer. We had a debate, actually 2 debates following the film. It was sold out, it was great. Next week we have an activity about the book club, which is online, which is about a person who fakes paintings. So it's called I Am Vermeer. And it's by a physicist who works with restoring art paintings. So it will be entertaining. And then that's on the 24th. On the 31st, we have an activity at a pub, which is, again, for the general public, which is about how to use mathematics to solve problems with epidemiology. So that's Roberto Krenkel from our institute. So we have lots of activities. You should stay tuned on our webpage for activities as they come up. So, of course, this activity is very special. We have David Gross, so it's hard to introduce a Nobel Prize winner. So he has a list of prizes, and usually the last prize you get is a Nobel Prize, and then, okay, but actually he got the prize 2 years after the Nobel Prize, which is he was named Doctor Honoris Causa of UNESP. And he's been here many times, so of course he's well known for his work, but he's also was the director of probably the most famous theoretical physics institute now, which is called KITP in Santa Barbara. So, of course, we are trying to imitate the things they do, and we decided to have this center. The first thing we did is consult with him to learn, what needs to be done. He's a frequent visitor here. This is already the 3rd time he's been here. And of course, he's on our search committee, so he's involved with our activities as well as with the activities of many centers around the world. So although he's famous for his work, of course, he's also very well known internationally for all the work he's done at science divulgation, especially theoretical physics. So the work he's going to talk about is, of course, QCD. But he's, of course, done many other things. Right now he's working on string theory, which is actually what I work on. And actually before he was working on QCD, he was involved in a project called the Bootstrap program, which was pioneered at a place called University of California at Berkeley, where I happened to do my PhD. So I intersected with actually his advisor, who was the father of this Bootstrap program. So for people who don't know what the Bootstrap program is, Bootstrap is just a strap on a boot. So it doesn't have anything to do with physics. But there's a phrase that people use, pull up by the bootstraps, which means essentially pull up without using anything else. So stand up without using anything else, which is, of course, impossible. If you're stuck in the mud and you only have your bootstrap, you're not going to be able to get out of the mud. But physicists have used that expression to mean trying to do things just from first principles, from consistency, from not requiring any other input. So people tried to understand the strong interactions using this, and essentially that idea was killed essentially by David Gross and the people who worked on QCD, where actually there is an input. It's a very simple input, but it essentially solves the problem with strong interactions. But about 10 years ago, these bootstrap ideas came back again. In fact, Pedro Vieira, who's our 6-month per year joint professor with Perimeter, was discussing with David about bootstrap. Now, of course, they have much more powerful methods to do bootstrap. Pedro is one of the leaders of the fields now. We organize activities on this all the time. So physics is like that. Sometimes you think you've found the right theory, and sometimes, well, maybe the oldest theory had some use anyways. So, okay, so this is something, of course, David knows much more than I do about, so I'll now leave it to David to tell about his work.
Well, thanks, Nathan, and welcome everybody. Good morning, or good afternoon, actually. It's great to be back here in Sao Paulo and at the IFT, and to see all these young faces. I'm going to tell you about a 50-year saga, past, present, and future, 50 years of QCD. And this year, indeed, is the 50th year anniversary of quantum chromodynamics, which is the theory of the strong nuclear force. So when I've been giving a bunch of talks around the world celebrating 50 years is a long time. When I see an audience like this, I realize that, you know, almost all of you were not alive 50 years ago. But even more, most of your parents weren't alive 50 years ago. So that's 50 years is a long time. It's almost 100 years since the invention of quantum mechanics. And maybe next year, the next year or two, we're going to be celebrating 100 years of quantum mechanics, which is another perhaps even bigger anniversary, changed our view of the world completely, dominates fundamental physics nowadays. So it's always interesting to look back. 50 years ago, I must say, if I thought about quantum mechanics, it seemed like infinitely far away. So 50 years, QCD must seem to most of you infinitely far away. So I'm going to tell you the story of how we got here and what the prospects for this theory are now. And let me start at the very beginning, which is even more than 100 years ago, with Rutherford, 1911, that's 110 years ago, who discovered the nucleus of atoms in an amazing experiment. This experiment that was carried out in 1911 deserved 3 Nobel Prizes. Rutherford got a Nobel Prize in chemistry, however, for his discovery and work on radioactivity. But unfortunately, he died rather young and didn't win another Nobel Prize in physics for this amazing experiment, which not only discovered the nucleus and revealed the structure of the atom, leading to quantum mechanics as we know it, and invented the experimental technique that has been used for high-energy physics, for fundamental physics for the last 110 years. So at least 3 Nobel Prizes for this work. What he did was he wanted to discover what the atom was made out of. And at that point, people had agreed that atoms are the basic constituents of ordinary matter, but they had no idea what the atom looked like. They knew there were electrons in the atom, but that was it. And Rutherford decided he would explore the structure of the atom by shooting alpha particles, which are the nuclei of helium, which he had studied the radioactive decay of heavy elements. So he could create a beam of alpha particles, which he shot at a gold foil in order to probe what gold atoms looked like. So his students, Marsden and Geiger, student and his postdoc, actually an undergraduate student and a postdoc, sat in a dark room for many hours until their eyes became instruments where they could detect the scintillations that the scattered alpha particles made on a scintillating screen. And they measured the deflection of alpha particles when they hit the atom. And so most people thought the atom was some kind of complicated, diffuse object, and most of the alpha particles would just pass through with slight deviations. Rutherford was very surprised that some of the alpha particles came back at him at large angles, and he concluded, using just electromagnetism, alpha particles are positively charged. The nucleus, as we know it, contains all the positive charge inside the atom, and it's localized in a very small region, the nucleus, and these alpha particles bounce off of it or scatter. And he could calculate the scattering cross-section, the probability that alpha particles would scatter in different angles. And from those calculations and the data, he concluded that inside the atom, all of the mass, just about all of the mass, most of the mass, and all of the positive charge was localized in a very small region, 1/100,000th the size of the atom. He could only put an upper bound on the size of the nucleus, but he determined that it was very small. And that obviously gave rise immediately to a planetary model of the atom. The nucleus was the sun, the electrons were the planets, and they had orbits around the nucleus. Of course, classically, that didn't make any sense because the electrons would radiate electromagnetic waves and fall into the nucleus, and in less than a second, all atoms would be unstable, and we would disappear in a burst of radiation. That led Bohr, only 2 years later, to propose a quantum model of the atom, the Bohr model, which was, as it turned out, to be a good approximation to the true theory, quantum mechanics, which was developed 10 years later in its final modern form without too much more experimental input. So Rutherford not only discovered the nucleus, which is the subject of our study today, unraveled the structure of the atom, leading to the Rutherford-Bohr model of the atom, which inevitably, its contradictions, to make sense of it, led to quantum mechanics. The nucleus, it took 10 years, 20 years before the neutron was discovered, which together with the proton make up the particles inside the nuclei of atoms. And finally, Rutherford, in this experiment, figured out how to probe ordinary matter at very short distances, how to construct a microscope that can probe nuclei and subnuclear physics. Today, of course, we have much better accelerators. So he just took a beam created from radioactive nuclei of alpha particles and smashed them on a gold foil. Today we smash protons on protons or electrons on electrons at enormously high energies to probe ordinary matter. But we have not improved on Rutherford's basic idea. In order to probe short distances, to figure out what happens at very short distances, you smash particles together, measure what comes out, and try to deduce what was going on at very short distances and what matter is made of and how it interacts. So he invented, in addition to discovering the nucleus, figuring out the atom, the experimental method that we still use today and conceptually have not improved on. We don't know any other way of studying matter at short distances. 3 Nobel Prizes. Unfortunately, he died rather young. Okay. So when I was a graduate student in Berkeley, University of California in Berkeley, which had the highest accelerator in the world at that time, 6 billion electron volts, 6 GeV, gigavolts of energy, 1 part in 1,000 of the accelerators we have today, but at that time it was the highest possible energy, and smashing protons together, or protons on protons, one was producing lots of new kinds of particles in addition to the neutron and proton. Situation was quite interesting. A lot of new experimental results, but there was no understanding at all of the nuclear force. And the strong nuclear force that held the nuclei together was especially intractable. The prevalent feeling was that it would take a very long time to understand the nuclear force because it was absolutely not clear what were the fundamental constituents of the nucleus. What were the atoms of the nucleus? Which particles were elementary? Proton and neutron seemed to be obvious from the beginning, but now the accelerators were producing dozens of new particles which looked very much the same. So which particles should we use to try to construct a theory of the nuclei? And then, what principle should we use? How should we construct the dynamics? There was no obvious principle. And even if you had a way of writing down by that time, a quantum mechanical, relativistic quantum mechanical, quantum field theoretic description of nuclei, how would you calculate? Because the force was strong. And when the force is strong, you can't just do simple calculations. When forces are weak, you can do simple calculations, perturbation techniques, but not if the stresses are formed. The prevalent feeling, as I said, was that it would take a very long time to understand the nuclear force. And famously, Freeman Dyson, who was one of the founders of the theory, the quantum field theory of electrodynamics, QED, very successful quantum mechanical version of Maxwell's theory of the electromagnetic field of electricity and magnetism, spent some years trying to construct a similar theory, quantum field theory of the strong interactions. Failed, gave up, moved to other things, and like many physicists who encounter a difficult problem and don't succeed at first, conclude that it's impossible to succeed, or it'll take forever, and so they can be excused in giving up, said that the correct theory will not be found for the next 100 years. He made that statement in 1960. It only took 13 years. But the prevalent feeling was that a revolution was needed. Somehow, you couldn't just quantize a theory because there was no theory to quantize, and how do you construct a theory? And there are many problems. In retrospect, the reason it was so difficult to construct a theory of the nuclear force was that the sources of the force, the charges that in the end turned out to be the sources of the fields that create the force, were hidden. The sources we now know are quarks, which carry charges, 3 charges, and they're not visible. No one has ever seen a quark moving across this room. The gluons, the quanta of the fields that hold them together, like the quanta of light, photons, also are not seen crossing this room. So the colored quarks and gluons, the charges of the force were completely hidden and invisible. And, you know, if you take an atom and hit it hard, then electrons fly out. You ionize the atom, and you know that those electrons are in the atom. They're part of the constituents of the atom. J. Thomson had discovered that in the 19th century. But when you smash protons together, all you got were proton-like objects, hadrons we call them, heavy particles. No quarks ever appeared in the... So quarks were in fact invented in the middle 60s to explain the flavor symmetries, the patterns of the hadrons that were being produced in accelerators, but were largely regarded as mathematical devices since they couldn't be produced in the laboratory. So they were just ways of accounting for the symmetries of hadrons. Even worse, the conceptual framework, the theoretical framework that existed at that time and was so successful in understanding in its non-relativistic version atoms and molecules, and its relativistic version quantum electrodynamics, quantization of Maxwell's theory, was under severe attack, especially in Berkeley, where I was a student. The reason for that was many. There were many reasons for that feeling that quantum field theory was deficient. One was that the success in the 1950s of quantizing the electromagnetic field required physicists to come to grips with infinities at short distances, infinities in trying to calculate physical observables that had to be understood and removed, since no experimentalist is ever going to measure an infinite quantity. And that there was a theory that was developed and understood of how to renormalize the theory and express physical observables in a finite fashion, which was very successful in quantum electrodynamics, but it was thought to be a trick. And most people were very unsatisfied with the whole program of renormalization, since it seemed to be a trick of sweeping infinities under the rug and an indication that something was truly wrong about quantum field theory, quantized field theory. Also, there were no real ways of calculating, nothing beyond perturbation theory, just using the fact that the electromagnetic theory, which is characterized by a dimensionless strength of interaction, 1 over 137, the fine structure constant. 1 over 137 is a small number, so you can expand in a power series in this small number. In fact, the first course I took in Berkeley, quantum field theory, was from Steven Weinberg, who was a great theoretical physicist who unfortunately just passed away last year. And he came into the class and wrote on the blackboard, field theory equals Feynman diagrams. Okay, that's clearly not the case, we understand now, and to understand most interesting quantum field theories, one needs a lot more than just Feynman diagrams, especially in a theory like QCD. But that was the state at the time. And since the strong interactions were small, perturbation theory wasn't useful. There was a theory, a quantum field theory, which today we would call an effective theory of the weak nuclear force. The weak nuclear force is responsible for radioactivity, and the Fermi theory of the weak interactions was a kind of effective field theory, which was moderately successful, but it was completely unclear how to make that into a sensible theory at high energies where the approximations broke down, how to unitorize it, how to renormalize it. Now, the secret lay in a non-abelian, non-commuting generalization of Maxwell's theory called Yang-Mills theory, which was invented in the 1950s in order to explore the possibility of Maxwell's symmetry. The underlying symmetry of Maxwell's theory of electromagnetism was a gauge symmetry based on the group, the abelian group U1, the rotations of a circle. The non-commuting or non-abelian version of that Yang and Mills gave was beautiful mathematically, but suffered from the problem that the quanta of that field, like the quanta of light, were massless, and nobody had ever observed such massless particles. So that was very mysterious for the next decade, but indeed people tried to apply this theory to the strong interactions as well. And in a gauge theory, like Maxwell's theory, you need charges. You need conserved charges. And there were approximate flavor symmetries of the strong interactions, which people tried to use to construct a Yang-Mills theory of the strong interactions. But it was realized very soon that it is simply nonsense to try to couple a gauge symmetry to non-existent symmetries, broken symmetries, like the flavor symmetries. So that didn't work. As Nathan remarked, Berkeley was the center of this attack on quantum field theory. My advisor, Jeffrey Chu, led that revolution, and his basis of his approach was twofold. One was something called nuclear democracy. So in these experiments, these colliders, you produce lots of heavy particles, which looked like the proton. They all seemed to be equally elementary, whatever that meant. And so the principle of nuclear democracy said all hadrons are equally fundamental. There aren't any elementary constituents of matter. I mean, maybe an infinite number of particles, you could regard any of them as elementary and the others as composites of those, or vice versa. And how do you construct a theory if you don't have elementary constituents? Well, this was the bootstrap approach. You don't write down a theory with elementary constituents and some kind of way of expressing the force between them, but rather you just demand that the observables, which are the scattering amplitudes, the probabilities that if you shoot two particles together, three particles come out at various angles, etc., that those amplitudes, probabilities, satisfy certain general principles that follow from sacred principles that we kind of believe in, like causality, you know, the cause precedes the effect and not vice versa, or unitarity. If you calculate probabilities for something to happen and add up all the different possibilities, you get probability 1. Something is going to happen. And based on those general principles, it's rather difficult to construct a consistent S-matrix, a consistent mathematical expression for these various probabilities in relativistic quantum mechanics, because in relativistic quantum mechanics, you can produce particles out of nothing with enough energy. E equals mc squared, if you want, plus quantum mechanics. So that was the bootstrap program. And I personally was intrigued, like many are, then and still now, by this program. But I must say, towards the end of my graduate study, I got pretty sick and tired of this, because you could plug in write down various equations that express these principles of causality and unitarity, and you stuck something in on the right-hand side and you got some constraints on the left-hand side of the equation, or vice versa, but there was nothing beyond that, it seemed. The effort still goes on today. It is not easy to construct these consistent relativistic theory, quantum mechanical theory, and the general constraints do play an enormous role in constraining the possibilities, but we now know that there are, in fact, an infinite number of possible consistent solutions. For example, QCD with any number of colors, number of charges, or quarks. Across the ocean, in the Soviet Union, there was another strong attack on quantum field theory by the Landau school. Landau was a great physicist in the Soviet Union who had enormous influence, and he and his collaborators studied what we would call the short distance behavior of electrodynamics, and discovered a problem that he thought destroyed quantum field theory. It was called the Landau pole, or the zero charge problem, which consisted of the following. In quantum field theory, in the old-fashioned way of constructing quantum field theories, one had to introduce some kind of cutoff to regulate the divergences that occur at short distances. And then you can calculate the physical charge that you measure, 1 over 137 if you want, fine structure constant, in terms of the coupling that is defined at the scale of the cutoff at very short distances. And what they discovered, at least in a simplified perturbative approach, was that in quantum electrodynamics, the bare coupling, the coupling at short distances, you calculate the physical coupling, no matter how big you make this bare coupling, the physics of screening, which I'll come to in a moment, ensures that you try to keep the physical coupling finite, the bare coupling blows up, is infinite. Not actually even before you get to arbitrarily short distances. This is the problem of zero charge. He concluded, this approximation at least, that you can't get a finite coupling theory. So this is the kind of formula that expresses the physical coupling in terms of the bare coupling and this cutoff, which should be taken to infinity. And you see that no matter how big you make E naught, if you let lambda go to infinity, this vanishes. Now, Landau was a bold physicist, very successful often in his boldness. And here he concluded, well, let me explain first the reason for this phenomena. It's simply screening, or dielectric, the effect of screening in a dielectric medium. Let's say you take the vacuum, an empty room, and you put a charge in that vacuum. Now, the vacuum isn't empty in quantum mechanics because you can create virtual pairs. There are always fluctuations in the vacuum. Electron-positron pairs pop out and disappear of the vacuum. So you have to, in quantum electrodynamics, in relativistic quantum field theory, regard the vacuum as being filled with virtual pairs of particles. And they act as little dipoles. And if you have a medium like this, you know, ordinary matter, you have such dipoles, and they screen the charge. In other words, they will tend to screen the charge, produce a dielectric constant. And that has the meaning of, in electrodynamics, of making the force that you feel due to this charge weaker because of this screening. And at larger distances, as you go out, there's more and more screening. Force gets weaker. At shorter distance, where there's less of this screening effect, the force gets stronger. So this is the effect of a screening medium in relativistic quantum mechanics. Your charge you put in is screened. The screening effect gets weaker at short distances. The force increases. And more screening at large distance, the force increases. This effect is real in QED. In fact, it's real in all what we now call non-asymptotically free theories, and probably means that they don't exist as for the same problem that Landau recognized. And he came to the conclusion that within the limits of formal electrodynamics, by which I think he meant quantum field theory, a point interaction, which means a local interaction, is equivalent for any intensity whatever, no matter how big you make this bare charge at short distances, to no interaction at all. And therefore, big leap of faith from a perturbative calculation to this conclusion that the Hamiltonian method, or quantum field theory, for strong interactions is dead and must be buried, although, of course, with deserved honor. Now, he didn't say that QED, quantum electrodynamics, was dead, because there the problem really only happens at extremely high energies. You can make this cutoff much, much bigger than the Planck scale or any imaginable scale of physics. You don't have to worry about this problem. But he knew that in the case of the strong interaction, the coupling begins very strong. And as you go to shorter and shorter distances, it'll get stronger. And very soon, it'll blow up. Make no sense. So he concluded that at least for the strong interactions, quantum field theory is no good. And he became a contributor to S-matrix theory, which did not involve quantum field theory. And he forbade his younger students to work on quantum field theory. And my good friends and colleagues, Polyakov, Migdal, people like that, continued to work on quantum field theory, but they had to disguise themselves as doing condensed matter physics. They had to say, we're not doing quantum field, we're doing condensed matter theory. Anyway, theory was in a mess, confused. Quantum field theory was being attacked. There was no real theory, but experiment was going strong. But here is also interesting history. There were many discoveries. Many new particles were being discovered every month. And they formed new patterns from which one began to get some, eventually, indication of what the fundamental constituents of matter were. But many experimenters and theorists believed that the secret of the strong interaction lay in the high energy behavior of scattering amplitudes. When you collide these particles, measure what comes out at very low momentum transfer. So if you collide two particles, most of what happens is particles, you get a spray of particles, but most of them go in the forward direction. Very few of them get big scattering, just like the case of Rutherford. And theorists started studying these high energy behavior and developed a whole theory called Reggie theory, which is very interesting, about what governs the very high energy forward scattering of particles. And experimenters loved that because that's where most of the data was. It was experimentally easy to do those experiments, measure the total cross-section or the diffraction scattering. And the theorists were discovering interesting patterns. And these perceptions of experimenters and theories reinforced each other. And nobody was very interested in the high momentum transfer, you know, where particles scatter backwards or at large angles, where it turns out the secret of the strong interactions was to be found. Now, my story, escaping from Berkeley, going to Harvard, where quantum field theory was allowed, I started working on what today would be called the short distance structure of currents, which are measurable objects, like the electromagnetic current that couples the charge of whatever it is that makes up the proton to electromagnetism, could be measured, and the behavior of these currents at short distances was something that could be studied, probed, and one could, as I did with Callan and others, make very simple, totally unjustified, but there was no theory anyway, assumptions about what happened when you brought these currents together. One of the interesting sum rules that Callan and I derived was based on something called the Sugawara model, which later played a role in string theory, which said that if you take a product of two currents at short distances, it's proportional to another current, the current of energy and momentum, the energy momentum tensor, and from that we could derive a sum rule, which actually turns out to be correct in QCD up to a constant, which we now can calculate. But it has the interesting fact that we didn't notice, but Bjorkane noticed, kind of implies scaling, dimensional scaling, that this cross-section, which enters into electron-proton scattering, is really a function only of this dimensionless ratio. Other sum rules we derived were abstracted from what we called the quark model. That was simply assuming that, okay, the electrically charged constituents of protons are quarks, this mathematical object that was introduced, mathematical particles, or they were introduced, and you could just take free field theory, assume these particles are completely free, then you could calculate easily. And the remarkable thing turned out that and a very easily measured observable, the ratio of the cross-sections for scattering of polarized light, longitudinal or transverse, depended critically on the spin of the constituent particles. If they were spin 1/2, you got transverse scattering only. If they were spin 0, it was just the opposite. So we could write down these sum rules. So I was very well poised and interested in what would happen at the new accelerator at SLAC, where for the first time the experimenters were scattering electrons off protons. Very much similar to Rutherford. He was trying to understand the structure of the atoms by scattering charged particles, alpha particles, off gold nuclei. Here, one was scattering electrons off protons to understand what made up the proton. What are the charged constituents of the proton? But, you know, this was a new accelerator. This was the first experiment. It was straightforward. One simply scattered electrons off protons and saw what comes out at large angles, not in the forward direction. Nobody was really interested in this experiment. The experimenters were all interested in using this new machine to discover new particles. In high-energy physics, elementary particle physics, experimenters wanted to discover bumps, new particles. But there were a few people who did this, and what they discovered was that the proton looks, in one interpretation of the results, were as if they were made out of freely moving quarks. So But what they saw was this scaling that Bjorkane had suggested, free point-like behavior, as we use to derive these sum rules. The quark model sum rules worked, indicating that the charged constituents of the proton had spin 1/2. So you needed 3 of them to make up a proton. Of course, proton is spin 1/2. And this is now recognized as the experimental discovery of quarks and was awarded the Nobel Prize in 1988 to these experimenters who did what, in retrospect, seems to be the obvious experiment. It's exactly what Rutherford did, and equally important in its implications. But it was incredibly confusing at the time, because the experiments and the sum rules convinced me, for example, and some of my colleagues, that hadrons were indeed made out of point-like constituents. It's the only way you could really explain that they looked like freely moving charged particles. And that the charged constituents were quarks. They had the quantum numbers, the properties of quarks, fractional electric charge, fractional baryon number, spin 1/2, etc. But quarks must interact strongly, otherwise you'd easily ionize the proton and get the quarks out. So how could you possibly explain that they were behaving like point-like, freely moving objects? So it's an obvious problem. Now, many of my colleagues said, okay, don't worry, the experiments have 20 to 30% error. They're really at very low energies. This is an interesting pattern, but you're reading much too much into it. It'll go away. But I sort of was convinced and started to study scaling. Now, scaling as a symmetry of nature is, today, it's at the root of much of our approach to fundamental physics. Scale invariance, the invariance of physics under change of scales, or its corollary in most theories of conformal invariance, even stronger. But nature is not scale invariant, right? You keep going down in scale, looks very different. At our scale, we got people. Go down by 10 orders of magnitude, we just have atoms. Go down by 18 orders of magnitude, we just, well, 10 orders of magnitude, we just have nucleons. Go down to 18 orders of magnitude, we just have quarks and gluons. Certainly not scale invariant. But it seemed to be at high energies or short distances, the theory became scale invariant. So it started the study of scaling as a symmetry in quantum field theory and in nature. But it was clear, indeed, that not just observation, but also theory said scale invariance is destroyed by quantum mechanics, if not by other things like the existence of definite scales in nature, masses, and so on. And these sum rules that we derived, scaling was clearly, completely broken by quantum effects. So how to understand this behavior. So I was totally intrigued by this confusion and paradoxes for many years, 5 or so years, but there was a detour in my efforts into the newly developed, at the same time, string theory, which was just arose 1969, 68, 69, and was another much more nuclear democratic way of trying to understand the strong interactions. But strings are soft. They're unlike point particles, which are very hard and point-like. Strings are soft, and they could not explain this scaling behavior that was observed. So by 1972, I had a plan, and the plan was to make my advisor happy by destroying quantum field theory. And the idea was to take scaling as a real physical phenomena, believe in the experiments, and prove that that required what we called asymptotic freedom. Namely, that unlike QED, the charge, the force between particles, gets weaker and weaker as you approach shorter and shorter distances, and eventually becomes zero. That's called asymptotic freedom. And that would explain scaling, because scaling is, the observed scaling is the phenomena that, as you look at the interaction of the, turns out to be quarks, constituents of protons, the force between them gets weaker as you go to shorter distances. But what we tried to prove was that that was necessary, not just sufficient. And with Callan building on some work of Parisi's, we showed that that was true for most quantum field theories that made sense. And the second part was to prove that there are no asymptotically free theories. And then I would say, okay, quantum field theory is indeed dead because of experiment and this argument. And Coleman and I proved, this all was around the same time, the late 72, 73, that no sensible quantum field theory with any number of scalar particles or spin 1/2 particles, by sensible, one meant renormalizable, one that could make sense with a finite number of parameters, or theories like QED could be asymptotically free. So the reason one could make such a remarkably strong argument was that asymptotic freedom means that at short distances, the coupling becomes arbitrarily weak, so you can do perturbation theory reliably, and the shorter you go, shorter distance you go, the better it becomes. And so sensible field theories are a countable set, and by countable arguments, you can prove the statement. The only part that was not proved here or here was these non-abelian generalizations of Maxwell's theory or Yang-Mills theory. And that was the final step to prove that no quantum field theory could explain the experiments. So there enters my first graduate student at Princeton. I was just a young assistant professor, and Frank actually was a student in the math department, but really interested in physics. And I said, well, let's calculate non-abelian gauge theories. And of course, what we discovered was that they were asymptotically free. Now, for me, that was a surprise. My intuition, like Landau, was that incorrect, that all theories have this kind of screening behavior and could not be asymptotically free, which was required to explain the experiment. But instead, we discovered that non-abelian gauge theories possess the remarkable feature, perhaps unique among renormalizable theories, of asymptotically approaching free field theory. And that could explain the behavior, deep inelastic scattering. One should look for a theory of the strong interactions to provide the explanation for scaling that eludes all other quantum field theories. To me, this was as I say, I've compared this to a message from a burning bush, Moses' experience. It was just surprising, but everything fell into place once we realized that. Because the theory you know, a non-abelian gauge theory of the strong interactions, there was really no choice. The dynamics had to be non-abelian gauge theory. That's the only theory that was asymptotically free. The force had to be mediated by these gluons, which are the quanta of this field theory with more than one charge. Gluons, which themselves were charged. Of course, a gluon, so it turns out, and we also knew that the matter had to be quarks, and we knew that quarks had to have 3 labels, degeneracy of 3. That came from various matching of simplified or later QCD calculations of pi decay, total E plus E minus cross-section, many indications that there had to be 3 colors. And so there was really no choice. You couldn't introduce other interactions because that would destroy the asymptotic freedom. You really had no choice but to introduce a theory with 3 kinds of fermions. We knew from experiment that there were 3 kinds of quarks, flavors of quarks. Each had 3 colors with an SU3 color gauge group to provide the strong interactions. There was really no choice. And that's QCD. Now, why does QCD not screen, but rather anti-screen color? So here, the best way of explaining that is a magnetic point of view. In electricity and magnetism, a relativistic theory, you can either think electrically or magnetically. Imagine a medium which contains little magnets, little permanent magnets. A gluon, the quanta of this chromodynamic field, has spin 1. Therefore, it's a little magnet. And the virtual gluons, which have this color charge as well, are also present in the quantum mechanical vacuum. And if you insert a magnet, a permanent magnet, into this vacuum, they will anti-screen. They will align with the magnet. And that's called paramagnetism. And its consequence is, if you think paramagnetically, the farther out you go, there's more magnets pointing in the same direction. The force increases at large distances, correspondingly decreases at short distances. So anti-screening is always present if you have virtual magnets in the vacuum. Now, the gluons, these charged gluons, are big magnets compared to the electrons, which are also magnets. And this anti-screening effect dominates over the screening effects of the charges, of the dipoles. I wonder why Landau didn't think of this. Landau was a great condensed matter physicist. He certainly knew about paramagnetism. He didn't, in his attack on quantum field theory, didn't, and because of the screening, did not say, okay, this is the problem of dielectric medium. What we need is a parametric medium, and then he could have been led to the same conclusion. Now, so he found the theory that could explain the short distance behavior, the fact that it looked like protons were made out of freely moving quarks at short distances. But what wasn't, second part of the confusion is, why don't you see the quarks? Why can't you ionize the proton? And here we had no, as you try to pull the quarks apart, you go into the large distance region where the coupling becomes strong. Certainly can't calculate easily, But it seemed reasonable to us to assume that this force would make it the case that the quarks could be completely confined, that there be no connection between the free theory, which has quarks and gluons moving around as free particles, and the asymptotic states that come out because you're in a regime of strong coupling. And this is what is sometimes called infrared slavery. It might be that the strong coupling that develops at large distances makes it impossible to see the quarks as real particles coming out. And this is what we believe is the case. So if you consider two charged particles in a theory like electromagnetism, you can use Gauss's law to calculate the nature of the force between them. It's the most fundamental way. Gauss's law states that the electric field at a distance radius r times the area of a sphere of radius r is equal to the charge inside the sphere. So that tells us that the electric field goes like 1 over r squared. You studied electromagnetism, you know that's Coulomb's law. And then if you try to calculate the work done to ionize a pair, a charge and an anti-charge, opposite charge, you take the force, the electric field, times the distance you move the charges apart and integrate 1 over r squared, you get 1 over r. So that means that with a finite energy, the ionization energy, you can pull the charges apart. What happens in QCD? In QCD, you have quarks, antiquarks. The antiparticle of a red quark is a red antiquark. Quarks are red, blue, and white, red, and blue, or whatever. And classically, the force between them would be given by the same kind of Coulomb's law. But the quantum vacuum, which is full of these virtual gluons, a virtual quantum chromodynamic field, this is a picture that comes from lattice gauge theory, a calculational device to calculate the fluctuations of the chromodynamic field in the vacuum. So you see it's a very complicated medium. Its effect is to squeeze these flux lines into a tube. Roughly speaking, this is the analog of the Meissner effect in a superconductor. A superconductor can be thought of as a medium which does not tolerate magnetic flux. And if you insert a magnetic field into a superconductor, the Meissner effect is that that flux that you've inserted, these lines that would be magnetic field lines, is squeezed to a tube. If you had magnetic monopoles in the world and you put them into a superconductor, they would be confined. The force between them would not decrease as you pulled them apart. And the analog of that, the dual analog, electromagnetic duality, analog of that is this flux tube in quantum chromodynamics, where the chromoelectric fields are squeezed to a flux tube. A flux tube whose area does not increase when you pull the quarks apart. And so that produces confinement by the same application of Gauss's law. If you now use Gauss's law to calculate the electric field due to this charge, you only have to integrate over this area, so E times this fixed area is the charge. The electric field does not vary with length. The energy increases with length. So it takes an infinite amount of energy to separate, to ionize a hadron, or meson in this case, made out of a quark and an antiquark. And that's what we call confinement. That explains, pictorially at least, how you could have a theory like this where quarks behave freely at short distances and move like free particles, but as you try to separate them, they're bound by a force that never decreases, and they're permanently confined inside nucleons. So the same phenomena, asymptotic freedom or confinement, fits together, and you, although we certainly are far from proving this, or even developing a controllable analytic, there's no question that this is what happens by now. We understand it physically in many ways. We verified it numerically on lattice QCD. And certainly experimentally, we've gone to energies which are 10, 100 times bigger in this last 50 years than before. And quarks have never been produced. This is a picture coming from lattice QCD of what happens when you separate a quark and an antiquark. You see the flux is confined to this flux tube, which, by the way, looks like a fat string. Not coincidentally, since string theory originated in an attempt to understand the dynamics of these mesons. And the data that came out of the scattering experiments had many features that were reminiscent of strings. And that's how string theory developed. This is a very deep feature of QCD, which I'll come back to. Now, just what happens when you have a new theory like this, which to some, certainly to me, but to many of my colleagues seemed, that's it. It was for a small group of physicists, which I call the smart physicists, it was immediately obvious that this was the answer, because everything that we had learned about the strong interactions fit into this kind of theory. And there were a few anomalies, which took some time to understand, but just about everything that had been learned for 60 years did fit into this theory by then. And furthermore, you could calculate. And in physics, new ideas gain traction when they provide easy calculations for large numbers of people. Of course, you want to do something interesting and fun and produce papers. So you could do a lot of calculations, especially at high energies and short distances where the coupling becomes weak, and you can use perturbation theory, which was by then being well understood, beginning to be well understood. But this is just a small group. Most physicists of my generation, or older, it was very interesting to observe. The older generation was intrigued, but they didn't understand quantum field theory as it was developing, and one needed to. The younger generation, especially those who grew up on the West Coast, didn't know any quantum field theory and assumed the experiments would go away anyway. But these smart people dominated in the end, and there was slow and steady growth in the acceptance of this theory with lots of interesting applications to experimentally testable regimes. There were also advances in theory, which were very important, because this is a weird kind of theory. It's a theory where you had elementary particles, which you could never see in the lab, except indirectly at short distances. One big advance was Wilson's lattice gauge theory. This is a truncation of the theory on a lattice, space-time, and which could then be studied numerically and non-perturbatively. And It exhibited string-like confinement at strong coupling. And if that could be pushed to weak coupling, because the coupling on the lattice really is the coupling at the lattice size, which must be taken to 0 eventually, a theory that was soluble in 2 dimensions and was asymptotically free and generated a dynamical mass gap was very reassuring to me that such a thing is possible and natural. Large N QCD in 2 dimensions was solved by Ed Hooft, which gave a soluble model of confinement, which looked a lot like what we imagined would happen in 4 dimensions, and many other developments. But the real clincher that convinced most people was this story of electron-positron annihilation. Now, this pictures the ratio of what happens to electron-positron come together. They can produce anything. This is the ratio of electron-positron to electron-positron, which is simple QED calculation, to what happened to electron-positron producing hadrons. And in a scaling model, this should be constant, this ratio. In a naive quark model, it should measure, if the quarks are the constituents of hadrons, it should measure how many quarks there are. And, well, we knew how many quarks there were. There were 3 quarks, 3 kinds of quarks, and 3 colors. So this was what was predicted, and it fit very well. The not very high energy electron-positron data until the spring of 1974. And I was at a conference at ICTP in Trieste talking about QCD and how it had to be the theory of the strong interactions, and Bert Richter gets up and points to this data, emphasizing these experiments at another new collider at SLAC, a storage ring where electron-positron collisions were observed. And he said, this isn't constant. It's increasing. So all these scaling arguments and QCD, I don't think he knew what QCD was, but is dead. Experimenters love this, love to kill theory. They've been very unlucky for the last 50 years. But well, they're not totally unlucky. They killed low-energy supersymmetry, or so they say. Now, the smart theorists knew that there had to be more quarks, at least one more quark, because the electroweak theory doesn't work unless you have another quark, the charmed quark. There are anomalies for SU2, electroweak symmetry, many indications. Theorists were rather shy back in 1974. Nowadays, they're incredibly arrogant because of the successes of the standard model in the last 50 years. But then they were shy. And very few people were, but there were good papers. Gayar and Lee, Ben Lee and Mary Gayar, Politzer and Georgi actually said if we get the charm, which should be around the corner, we should see narrow charmonium charm-anti-charm states because of asymptotic freedom. Because the coupling gets small, you can treat these bound states of charm-anti-charm, which would be at short distances, much like atoms, and calculate their width. They should be narrow. But they didn't, they were shy, tentative. Theory hadn't been very successful for so many years. It's just beginning to be successful. And Richter was. But then he went back to Stanford, and a few months later, this is what happened, as you all know. Charm was discovered. Very narrow resonances, which indicated many other suggestions which were total nonsense, but in the end, the obvious conclusion was that you reached the charm threshold, a new quark was entering that could be produced at short distances, bound states of that new quark were formed, and there was a whole spectrum of such heavy quark bound states that could be analyzed using QCD, great success, and that, of course, has continued over the last 5 decades, discovering two new quarks, bottom quark, new vector mesons with a weak interaction, and so on. Completely consistent with QCD. And that's the kind of thing, historically, convinces people because there's a challenge, but it turns out, okay, actually, it's a triumph. Now, what about the direct tests of this phenomena? Well, this is the way it stood in 1989, which is 16 years later. This is the experimental results that measure the decrease of the coupling of QCD as you go to higher energies or shorter distances. Well, it looks in agreement. These lines are the theoretical errors at the time. These are the experimental points. It kind of agrees. But, so does a straight line. It's really hard, these precision tests of QCD, because this is a very weak effect. It's logarithmic. The decrease of the coupling goes like that. So this is on a log plot, right? See, it's very hard. This is today, well, later. This is 40 years later. Pretty good, very good, in fact. This is the tests of the deviations from scaling. So this scaling behavior that motivated this direction is not exact because you're only approaching zero coupling. And so there are logarithmic corrections that can be measured, but it takes very high precision, high energy experiments. Today, most of what goes on at LHC, 99.9%, is QCD scattering events, which can be calculated now with incredibly high theoretical and experimental precision. And this is the agreement, if you want, of the decrease of the coupling asymptotic freedom, which is now tested at a less than 1% level. And you can actually measure now the coupling, the strength of the coupling at this scale of the 100 or so GeV of the strong interaction coupling. And the deep elastic scattering tests are incredibly good. And LHC now provides literally dozens, if not hundreds, of better than 1% precision tests of the theory. So, experimental tests are there, no doubt. But theorists, what I really wanted to do as soon as possible after the theory was developed was to use it to calculate, on pieces of paper with the mass spectrum, for example, of the hadrons. But that's a hard problem because, to get these bound states of quarks which are only bound because the interaction is strong, you can't just use perturbation theory. You need something like lattice QCD, which remains our only tool for precise, controllable first principle calculations of, for example, the masses of the elementary particles we observe. Now, lattice QCD was proposed, as I said, in 1974, almost 50 years ago. Today, it is an incredibly high precision tool for calculating a priori properties of hadrons, of nuclei. But it took 50 years, or 40 years perhaps, and an increase by some a calculation of a factor of 10 to the 18 in computing power. Not just computing power, Moore's law accounts for maybe 10 to the 9 increase in our ability to control lattice QCD, but another factor of 10 to the 9 in advances in understanding how to numerically simulate a quantum field theory on a lattice, and all sorts of clever algorithms and theoretical advances. So both of these factors of 10 to the 9 of a billion times a billion have really been required to turn lattice QCD over 50 years into a precise calculational tool. And now we can calculate the mass spectrum of hadrons, all these particles that were being discovered and many more heavy quark states to 1% accuracy. Can even calculate a priori the mass difference between the neutron and the proton, which luckily comes out right. The neutron is heavier than the proton. If it was lighter, we wouldn't be alive. All our protons would decay. But we can calculate that from first principles now to, again, a few percent accuracy. It's quite remarkable. And also, the calculations, the perturbative calculations, which drove the theory from the beginning, have been now vastly improved. So this was what we calculated, the first term in the beta function, which tells you how the coupling behaves as a function of distance. But now there are calculations up to fifth order amplitudes. These scattering amplitudes at high energies can be calculated perturbatively, but these are hard calculations if you want to go beyond leading order, which we calculated. It was rather easy. But go to next to leading order, next to leading order, next to leading order, where people are roughly now, and is needed to have these high precision tests of QCD at the LHC. Not just to test QCD, but to understand the background for new physics that you can only discover if you can subtract out the background. For example, the Higgs particle could never have been discovered without understanding the background to this little small bump that appeared on top of the calculable background. And in being able to do these calculations, it was necessary and remarkably turned out to be the case that things are QCD is a very beautiful structural theory whose perturbative expansion has amazing mathematical properties, which many people believe might be indications of a deeper structure that we haven't yet understood. Now, I'd like to say words about this theory, which I'm very proud of, a perfect theory. And what its perfect attributes are threefold. First of all, it really has no infinities. All these ultraviolet infinities that were swept under the rug that made people doubt quantum field theory don't really exist. Second, it has no adjustable parameters. I'll explain what that means. And finally, it's the first theory we've had, fundamental theory, which has no indication of a problem if you go to arbitrarily short distances or high energies. And all of these have important implications. So first of all, there are no real divergences. I talked about the bare coupling that has to be introduced. Well, on the lattice, you have a well-defined way of defining QCD by putting it on a lattice, introducing a coupling at the lattice scale, and then taking that lattice scale to zero, constructing a continuum theory. That's how you do calculations in lattice QCD. The theory tells you that that lattice coupling at this distance, when you let A go to zero, take the continuum limit, behaves in a calculable way, asymptotic freedom, vanishes logarithmically, and that's how you take this well-defined integral, it's a highly many million-fold integral, but you can take a to 0, finite volume, and take the volume to infinity, and then if you take the coupling to 0, physical quantities remain finite. In this kind of calculation or definition of the theory, there are no ultraviolet infinities ever. The coupling, bare coupling vanishes in this limit. The physical couplings remain finite and calculable. No infinities at all. No ultraviolet problems. The ultraviolet infinities only occur if you try to measure, relate things at finite distances, which is where we do experiments, right, to objects that would be measured at infinitely small distances. So you get an infinity if you divide a number by 0, but you don't have to. You just calculate physical observables. Infinities never occur. So all of the problems of the founders of quantum field theory, which were very disturbed by these ultraviolet divergences and believed some revolution was needed, not the case. Second, there are no adjustable parameters. Now, recently I read a very beautiful article by Feynman at the Solvay conference in 1961, where he reviewed quantum electrodynamics. So at this time, quantum electrodynamics was developed in the 1950s. Renormalization theory, he reviewed the whole subject. QED worked beautifully, agreed with experiment. Then he wondered, could I make this into a complete, satisfactorily complete theory? And what he wanted to do was explain the two parameters that characterize QED. One is the mass of the electron, which had to be put into the theory, and the fine structure constant, 1 over 137. So he said, well, let's imagine we have pure QED with 0 mass electrons. Could we, on the one hand, produce a massive electron, somehow dynamically, and on the other hand, calculate the fine structure constant? So like all physicists, he was greedy or ambitious. So he said, okay, just consider pure QED, only 0 mass electrons, interacting with no other particles, having no cutoff energy. Sorry. But he says it cannot produce an electron mass. Now, there are two reasons why such a theory couldn't produce an electron mass. One is chiral symmetry. But Feynman already understood at this point, due to the work of Nambu, which he cites, that chiral symmetry could be broken spontaneously and you could get a mass. But then he says scale invariance. Well, the theory has no scale. There's no mass. Fine structure constant is dimensionless. So how can you produce a mass? Because that involves a scale. So the theory is invariant to a change of scale. There is no possibility to determine a length. Yet an electron with a mass involves such a length, and he concluded, I'm not certain. Feynman was always careful. But it appears to me impossible to produce a specific length from a theory which has no scale whatsoever. Well, we've just been discussing the same problem. Quantum field theories always have a scale due to these quantum effects of screening, which are scale dependent. He concluded you cannot calculate the mass of the electron or alpha. This can't be a theory which calculates everything. But quantum effects do break scale invariance, can produce a physical mass, and determine the coupling, and that's what QCD does. It in essence, has no adjustable parameters. Now, to make that argument precise, I have to do what Feynman did and ignore the quark masses, which are determined, we now know, by other physics, the Higgs sector, and are irrelevant for QCD. So let's take the quarks to be zero mass particles. It will have no effect on the proton. If the quark's at zero mass, your weight wouldn't change by more than a few percent. So what happens is called dimensional transmutation. To define the theory, as I said, for example, as a limit of a lattice theory, you have to introduce a scale. That's where the scale enters into the theory, but nothing depends on that scale. And this is the argument that tells you, and I'm not going to go through it, that any physical quantity, its dependence on the coupling of the theory and the scale is determined by one function, which tells you that the physics doesn't depend on this arbitrary scale you've introduced. And in terms of that one dynamically produced scale, say the mass of some particle you choose to define the scale of masses. To do measurements, you have to define a scale, right? When you measure the mass of a particle, you say that it weighs such and such times the mass of a, well, it used to be an object that was in Paris someplace, you know, define the kilogram. Here, today we say it's really the mass of the proton or of carbon atoms or something. Anyway, so in QCD, there are no adjustable parameters. For example, consider the proton. A rough approximation of the proton, even if there were quarks had no mass, would be these massless particles rattling around in a region of space which is determined by the strength of the coupling, right? The quarks, if you try to pull them outside of this region, the force between them is so strong that they are confined. So the proton is a confined quark, massless quarks, say, or very light quarks and massless gluons, confined to a region of space which is determined by the size of the coupling. And if you fix that mass to be your standard, say the mass of the proton, then you determine the coupling. And once you've determined that scale and coupling, all other masses are calculable. All mass ratios, dimensionless numbers, that is what we actually measure in the real world, are calculable numbers. So QCD does achieve exactly what Feynman was trying to achieve in QED, where it's impossible, to have a theory in which there are no adjustable parameters. All dimensionless, measurable physical quantities are calculable, and by now are being calculated. And the strong coupling at this size is calculable. Now, perhaps the most important, however, feature of this perfect-ish theory is that it tells you that there is no, really, in QCD, no new physics at short distances or high energies. On the contrary, asymptotic freedom means that QCD becomes simpler and simpler, and you can use perturbation theory, and it becomes better and better. And the immediate consequence of that was to cosmology. So astrophysicists at that time were, this was CMB, cosmic microwave background radiation, was discovered in 1964, 65. People had now to try to understand an expanding universe. What was the history of the universe? If you go back with the expansion, the universe gets denser and denser, and that's what they wanted to explore. But before, they were faced with what one of my colleagues called a hadron hell, namely complicated nuclear physics. So CMB, 3,700 years after the Big Bang, was a gas of freely moving electrons and photons and so on. But if you extrapolated backward, it got denser and hotter, you'd have nuclei and nuclear physics, and nobody knew how to do anything. But QCD told you, no, it was just a quark soup. If you go back to early times, there will be things will get simpler. Not only will they get simpler, there will be a phase transition where the quarks confined in nuclei the nucleons will melt at a high enough temperature or density into free quarks and gluons, some kind of quark-gluon plasma, and that could be treated perturbatively, or however, at least one had understanding of all of the particle physics that would ensue and allowed cosmologists to go back, as we do now, not just to a few 100,000 years after the Big Bang, but within micro, milli, nanoseconds of the Big Bang. And of course, this understanding of the possible phase transition of quarks, of nuclei and quarks, gave rise to an incredibly alive subject of nuclear matter, quark matter, as one varies the density, either in cosmology or in neutron stars, and the temperature, either in cosmology or in high-energy collisions of nuclei, where you create a kind of fireball of nucleons, which at a high enough temperature, high enough density, we believe, undergo a phase transition to quark matter, freely moving quarks. And finally, the fact that the strong interactions got weaker at high energies means you could extrapolate the standard model way beyond what is measured today to higher and higher energies. Things only got simpler. And what was discovered shortly after the completion of the standard model around this time was that just simple extrapolation, perturbative extrapolation, forces are all rather weak once you get to high enough energy, indicated, as did the particle content of the standard model, that there was unification at a very high energy. This is a logarithmic scale, so you have to go to very high energy before the strength of these forces unify, which happen to be close to where gravity becomes a strong force. Gravity is very weak at low energies, but its charge is energy or mass, so it increases rapidly, and at this scale suggests unification of all the forces we observe in nature, and has led to that observation, that clue, continues to be, in my opinion, the most important clue we have about what goes on at a fundamental level. And certainly the motivation for string theory, which is gives us tools to explore theories that unify gravity and the other interactions. By the way, this also explains one of Dirac's large number problems. You know, in physics, there are enormous differences of scale in some quantities. The universe is big compared to an atom. The proton is very light compared to the natural scale of fundamental physics formed out of the three basic dimensional parameters: the velocity of light, the Planck's constant of quanta and Newton's gravitational constant, which gives us the Planck mass. The proton is very light compared to the natural scale of physics. Everybody thinks it's light compared to the Planck mass. This 10 to the minus 19 is an intriguingly small number, hard to imagine understanding. And Dirac pointed out that there are lots of these very large numbers, roughly all like 10 to the minus 20 or 10 to the minus 20 squared, the radius of the universe compared to the radius of the atom. He could have said, okay, these numbers are what they are because we exist. There are people who play these anthropic games and say some features of what we observe in nature are there just so that we can exist, or turn it around. There are many kinds of physical worlds that could exist, and the fact that we are here tells us that we're in one of these worlds where this number is very small. This number were 10 to the minus 1,000, 10 to the minus 3, 1 over 1,000. It's a small number too, but it would mean that if you take 1,000 nuclei and put them together, not to speak of 10 to the 23 nuclei, and you would form a black hole. So if this number were reasonably small, then we wouldn't exist because we would all be black holes. That's an argument why this number better be very small if you believe in anthropic arguments. Dirac was much too smart to do that. But what he did do was try to relate all these small numbers. And he said, okay, there are a lot of other small numbers like the size of the universe in atomic units. And all these small numbers are related. And one implication of that was very clever. Some of these numbers vary in time, like the universe gets bigger, atoms remain the same size. So these ratios change. Maybe they should all change. He said, therefore, things like Newton's constant or the fine structure constant might vary in time, very slowly, but over cosmological times. That, by the way, has been largely ruled out. It's amazing. Physicists can say, you know, fine structure constant hasn't varied by 10% over the last billion years. You might think about how they come to that conclusion. And our hint is billion-year-old nuclear reactors. But think about it. Anyway, that problem is solved by QCD, at least conceptually. Because, you know, this decrease in coupling logarithmically tells us that if we really have a unified theory at the Planck scale, this very high energy scale, and the coupling is sort of what you'd get from electromagnetism or from data, from what we know. And you ask, well, where is the proton going to be formed? Well, its size will be determined, its energy, its mass will be determined by the point where the coupling becomes strongish. And since that's a logarithmic variation, the ratio of the proton mass to this Planck mass, this fundamental scale, should go like e to the minus 1 over the coupling squared. And that roughly gives 10 to the minus 19, or 19 plus or minus 2. That's probably the answer why the proton is so small. We don't have an answer for few other very small numbers like the cosmological constant, perhaps. But this number we understand conceptually, and that I think is a great achievement. So QCD is the first example of a complete theory, no adjustable parameters, no indication where the theory would break down, and that's what I call a perfect theory, infinite bandwidth. Now, of course, there are parameters in the theory. It said 3 colors, Y3, could be 5, could be 4, could be 1,000,000. Actually, if it was 1,000,000, life would, for us theorists, would be a lot easier. Why are there 6 kinds of quarks? They have masses. Where do they come from? So even within a perfect theory like this, if you ignore this, there are all these undetermined features. And of course, there's the real world with other forces and gravity. Now, let me end with a discussion of this fact that we see with QCD of mesons forming strings. This is the connection between string theory, QCD flux tubes, and open strings in string theory, which was invented to explain some of the phenomenological features of the strong interactions. This connection is very deep, very fundamental. Gauge theory and string theory appear to be 2 sides of the same physics, and we now have many examples where this is quite precise. But one thing that emerged immediately from string theory, also from QCD in a slightly different way, but anyway, is once you have open strings like this, which describe flux tubes, you have closed strings, and they, turns out, in fundamental string theory, describe gravity. They're the quanta of gravity, of gravitons. This gives rise to one of the main hopes of finally solving analytically, not numerically, with lattice gauge theory, QCD. And one of the hopes that remains is when you do take this number of colors, not to be 3, but to be infinite, QCD simplifies. It is, you can show, a non-interacting theory of glue balls. When the number of colors is infinite, you can ignore the quarks. You just have these gluons. They can form states. And when NC goes to infinity, you have an infinite number of stable states. This is a theory which, in a sense, is described by some kind of classical theory, non-interacting classical theory, where the number of colors is something like 1 over the h bar going to 0 being the classical limit. And it is most likely a string theory. It has all the features, many features of a string theory. So the evidence for this comes from the perturbative expansion of QCD, from the fact that this kind of expansion is quite good phenomenologically, and from a powerful duality we have learned, and which has dominated fundamental physics for the last 25 years, of a duality, a precise duality between open strings and closed strings, or quantum field theory in flat space, the kind we use to describe ordinary materials, QCD in particular, and strings in a anti-de Sitter space. So the hope that drives many of us is that we could, for example, solve this precisely dual theory to string theory in anti-de Sitter space, which is a highly supersymmetric gauge theory and string theory. This has almost been achieved to some extent, some parts of it. And then using this interability or solubility of the theory and the dual string theory, deform that theory to QCD and get an analytic description of real QCD. Let me end with a few remarks about the future of QCD. Now, QCD is a theory that's going to remain in its domain. Of course, it's only part of the complete final story, but nuclear physics is going to remain for centuries. The future prospects are perturbative, numerical, and analytical, and experimental. Perturbatively, enormous progress has been made and will continue to be made in understanding the perturbative expansion, maybe with deep lessons about some of the deeper questions of the analogy with string theory, which addresses deep questions of quantum gravity and the like. Numerically, lattice gauge theory is an incredibly powerful tool, but it only is useful for static properties like the masses of elementary particles, and not for calculating scattering amplitudes, time dependent. There are new powerful techniques which are being developed and with quantum computers will exist in the future that will enable perfection of these tools and be able to address perhaps questions that are still quite unsolved within QCD. And then there are experiments, as always, will be very important. And there are many experiments going on which are illuminating different aspects of quantum chromodynamics. LHC, in addition to testing QCD and these scattering experiments, has discovered dozens of new quark states, some of them quite exotic in terms of the old, the traditional way of thinking about quark bound states, made perhaps of 4 or 5 quarks. And they continue to discover these new states all the time. They're really quite fascinating. We can recreate the situation in the early universe by smashing nuclei together at very high energies, creating these fireballs with large temperature, large average energy of the quarks inside the nuclei, and observe phase transitions to a deconfined phase of quarks and gluons. Very interesting state of quantum matter that is produced here, a kind of perfect quantum fluid of quarks and gluons. Even higher energies presumably becomes a quark-gluon plasma. Very interesting. There's a new experiment going to occur at Brookhaven, an electron-proton accelerator, where, much like at SLAC, deep inelastic scattering experiment, where electrons will probe the structure of protons at even shorter distances and of nuclei. And nuclear physics is now becoming a branch of QCD, if you want to understand nuclei and nuclear physics on the basis of quarks and gluons. So let me try to summarize what we've learned over these 50 years. Now, Feynman once made the following beautiful summary of physics. He asked, what happens in some cataclysm? And all of scientific knowledge was destroyed, and only one sentence was passed on to the next generation of creatures, either cockroaches or chat GPTs or whatever. What statement would contain the most information in the fewest words about our modern understanding of physics? One sentence. That's really tough. And he said, I believe it's the atomic hypothesis, the atomic fact, whatever you want to call it. He said, all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another. I can't imagine doing better than this. One sentence, if you know a bit about physics, you can understand the cockroaches trying to understand this and developing a lot of modern physics based on this one sentence. So anyway, I tried to summarize what have we learned from the standard model in the last 50 years. Standard model is not just QCD, but electroweak electromagnetism, and the Higgs. Well, I couldn't do it on one sentence, but I can do it on one slide. We've learned that matter is made out of charged spin 1/2 fermions. Forces are described by gauged quantum field theory, which exists in 3 phases: electromagnetism, Coulomb long range, unbroken gauge symmetry, the weak interactions, which are screened or Higgsed by an unnatural scalar sector, and SU3 strong interactions, which are in the confined phase. That's one slide of the Standard Model. After 50 years, what have we learned about QCD? Well, the most important lesson, of course, is that QCD is the theory of the strong nuclear force. We've learned that, what I was stressing before, that it is possible to have a theory where the dynamics determines all dimensionful parameters, all masses and couplings. That raises a strong challenge for any subsequent theory. If you can't do this, come on, you're not doing better than the QCD. So this, I think, is a quite remarkable feature. But the most important thing is this duality with strings. And I believe that if we look back 50 years from now, rather if you look back 50 years from now, the real hero of all of this is non-abelian gauge theories, these generalizations of Maxwell's theory, which are the secret for QCD and the rest of the Standard Model, and are dual to strings and to string theory, which is the secret behind the dynamical structure of space-time, which we're beginning to explore. So with that, I come to the end, but not the end of QCD. I really went over. And I apologize for slightly going over my time.
So we'll invite him back to finish his lecture later. But let's have time for questions now. So I guess let's say 15 minutes for questions, and then there's some refreshments for people afterwards. So go ahead, you can start.
Hello.
Nathan, back there.
Go ahead. Yep.
Hey, Professor. Thank you for the talk. And I'm interested in talking about the attack on quantum field theory that you said happened in the 70s, and some could say it's happening in the 60s, and some could say it's happening again now, because as you mentioned in passing, supersymmetry at low energy didn't find anything. People are poking holes, experimentally trying to poke holes at the Standard Model, the recent Fermi result, and etc. And in the recent years, there is some people trying to understand those old problems, those old critiques of infinities and problems in fundamental quantum field theory from the perspective of foundations of quantum mechanics. That there are problems in the foundations of quantum mechanics that somehow could lead to these fundamental problems in quantum field theory. I would like to know what's your take on that, and what would be your take on these recent attacks on quantum field theory, if you think there are?
Well, actually, I don't. Well, so you mentioned a few things. Low energy supersymmetry is a speculation that, is under severe experimental attack, not theoretical. Many things are possible within our speculative thinking about going beyond the Standard Model. and experimenters' role is to rule out many of our ideas. So that's natural, and it doesn't threaten either theory. Well, it threatens one possible explanation that was given to a problem that we have. I mentioned Dirac's large number problem. There are other large number problems or small number problems, such as the mass of the Higgs particle, which is kind of light, again, compared to the Planck mass. And one solution of that was low energy supersymmetry, which, by the way, hasn't been ruled out. But, okay, theorists, one of the explanations of theorists that was very attractive for many reasons turns out to be false. That's how science progresses. We've learned a lot. But that doesn't threaten quantum field theory or anything else. It just says, to a theorist, you have to work harder. The other experimenters are indeed trying to find holes in the standard theory, as they should, always, and that's their job. And but so far, to some extent, unfortunately, because we know there are problems that do require us to go beyond the standard framework, even at energies low compared to the Planck scale, are unfortunate. We'd like to get direct experimental evidence. The Fermilab G-2, I don't think is a problem. It seems that the better theoretical results that are calculations that are emerging are totally consistent with that. So unfortunately, there's very little experimental evidence for new physics, except to rule out certain theoretical speculations, which is great. As far as foundational questions in quantum mechanics, which have been asked now for 100 years, I don't think they're any more threatening than they were 100 years ago. And I see no issues there. The real conceptual threats are ones that we're beginning to engage with, and they mostly have to do with constructing a quantum mechanical theory of dynamical space-time, of quantum gravity, and its relation to the other forces. And there we're really beginning to finally have the tools to attack such conceptual issues and resolve some of them and make real progress. And that's very exciting. But quantum field theory in its realm is under no threat that I can see.
Thanks for the lecture. I'd like to know your thoughts on information theory and how quantum information can help us better understand QCD.
Yeah, well, thinking about information is often very informative. It definitely, well, this is related to a general, I think, conceptual development that's been occurring for 100 years and partly connects to the last question, which is understanding quantum mechanics better. So it's really hard sometimes to learn to live in Hilbert space. It's a strange place. We're macroscopically accustomed to ordinary classical phase space. And my opinion is that we don't truly, there are many aspects of quantum mechanical systems that, especially with many degrees of freedom, like in condensed matter physics or certainly in high energy physics, fundamental physics, that we're just beginning to understand at a deep level. And the properties of quantum systems in general, including the information content of quantum states and entangled states is very aclassical, non-classical, and different. And I think in general, it's the recent improved understanding of quantum states in general has enormous, will greatly advance our understanding of quantum mechanics as such and of real physical systems, including ordinary many-body systems, condensed matter systems, but even more so in the case of dynamical systems of space and time.
Okay, thanks.
Thank you for the lecture. You talk a little bit about lattice QCD, and I would like to hear, it's not a question, but I would like to hear a little comment about your opinions regarding some problems, despite the fact that lattice QCD is one of the main tools that we have to retrieve observables and informations about the static QCD. So we have some problems regarding, for example, the sign problem and putting fermions on the lattice. So I would like to hear a little bit from you about these questions, these modern questions about lattice QCD.
So this is a problem because theorists haven't been smart enough or lucky enough.
Yeah, for sure.
But it's a great challenge, especially to young people. There are a whole bunch of absolutely fascinating physical questions in any theory with many degrees of freedom, many-body theory, but certainly QCD, which lack well-defined numerical techniques. And the sign problem, which afflicts attempts to take a lattice approach, so far haven't been solved. I don't know, for people have been thinking about it for 40 years or more. But it's a big challenge. There is an opportunity to develop some new numerical techniques, calculational techniques, which could have enormous implications for condensed matter physics, for QCD, for any quantum system. So people imagine quantum computers solving the problem, which might indeed help. You could imagine that. Quantum simulator solving the problem, or other techniques. But I would most likely predict that the real breakthrough hasn't yet happened. Somebody needs a good idea. And of course, if I had it, I would tell you what it was, but I don't. But you might. It really is, there are a lot of enormous number of open problems that could be tackled once one knows how to solve the sign problem, if you want.
Hello, thanks for the lecture. You told us about in the 60s, people say that the QCD was dead and things like that. And nowadays, a great part of the community says that the string theory are dead. And I would like to know what your opinion about the string theory nowadays and what will be the future of the theory.
Well, so let's go back now, not 50 years, but 40 years. 40 years next year is sort of the anniversary of the string, the second string or revolution, if you want, which turned string theory into a pursuit of a few people into a major enterprise. So that was enormously exciting because it was realized that one could construct well-defined, sensible theories that had all the ingredients one needed to provide a complete theory of all the forces we knew about and understood in the standard model and quantum gravity and so on and so on. And not only that, what was most attractive, at least to me, was that, taking QCD as an example of a perfect theory with no adjustable parameters means you could calculate everything. String theory appeared to be the first theory where all parameters that you might introduce in theory were actually dynamical. They weren't numbers that you had to measure. They were dynamical fields or dynamical degrees of freedom. So that offered a way of imagining getting not just a theory that contained everything that we so far observe and understand, but actually calculating everything, the ultimate goal of physics. So it's a very exciting, and understandably, some of us got, very excited. The end is near. But as is often the case in physics, when you have some breakthrough, some new kind of thing, then you realize, well, it's not just this one possibility. There is a whole manifold of possibilities. We realize that string theory is much more complicated and complex. It's not really a theory anyway, just a whole bunch of approaches to constructing consistent quantum realizations of. And now we understand that it's not really different than quantum field theory. It's dual often to quantum field theory. And we're far from understanding the final end of the story. But to say that string theory is dead is silly. It's just that the over-optimistic or enthusiastic hopes have turned out to be much more realistic than we'd hoped. It's far from dead. It's incredibly alive and interesting and beginning to deal with, the real conceptual issues at the heart of quantizing gravity or understanding the quantum dynamics of space and time. So
just last question, and then, of course, David will still be around, but we'll have a break for refreshments.
So thank you for the lecture and for your inspiring presence here in our institute. So my question is, speaking of inspiration, to discover QCD, you and collaborators were actually tackling some problems and also looking at some experiments. So my question is, for us young physicists, what are the experiments with the pressure issues of QCD we should be looking?
Well, in QCD, sorry, you asked about QCD or not?
Maybe if you want to ask a broader question, it's...
Well, there are, it's a very different period. It's really, so at the time, theory experiment was completely dominant, making discoveries every day, every month, and theory was completely impotent. Today, it's sort of the opposite. Experimental discoveries get harder and harder to achieve. What I call the curse of logarithms. Mm-hmm. Physics evolves logarithmically, we see it, once you get to a certain distance scale. Whereas the cost of exploring that regime increases like some high power of the energy in dollars. So experiments get harder and harder. But there are experimental facts, if you want to call them discoveries. They've been around for some time that are very mysterious. A lot of them have been discovered not in collider experiments, but in astronomy and cosmology. The expansion of the universe, the accelerated expansion of the universe, the cosmological constant. The beginning of the universe, which we're beginning to get closer to need to understand. The existence of dark matter. So these are fundamental measurements that whose implications are not understood, and the fact that some of them have been around for 30 years or more doesn't make them less interesting. And then there are all the mysteries that remain in the standard model, the crazy quark mass spectrum of 9 orders of magnitude. Where does that come from? And the Higgs sector, which we're just beginning to explore, and there are so many questions. So many of them have been around for 30, 40 years, some more recent, and people have tried to do many, many attempts to solve them, and haven't succeeded, or have only partially succeeded, or might succeed. But it's a mistake for young physicists to ignore these problems simply because there have been 40 years of their teachers being unable to solve them. They should go back and say, okay, my teachers are stupid, and I can solve these problems, and try. So these are really profound problems. And the fact they haven't been solved for 40 years might mean 2 things. One, lack some new experimental clues, or lack some new ideas. But if it's a second, well, that's room to come up with new ideas.
Thank you.
Okay, so let's thank David again for a wonderful lecture.